vector equation actually. So it's good for both x and y. So we can write a vector equation that way. And instead of x and y separately, we can have a vector equation. That way it's a terse expression for both the x and y coordinate. And when you take a derivative, it's going to be also a vector equation. And this is then saying that if I have these two balls as a system and I throw it, as a system, the total momentum is the total mass times the velocity of one point. That is the center. Velocity of the center. Okay. Which may not be where either of the balls here. Okay. So the center mass is here. And that's the total momentum of this system. Or you can find the momentum of one of the ball, momentum of the other ball, add them up to get the total momentum of the system. So you get the total momentum two ways. One, you do it individually and then add the vector sum. Or you can do the total mass of the system and just consider the velocity of the center. The next step, you take another derivative. Velocity depends on time, so you get the as far as the system is concerned, total mass times the acceleration of one point, that is the center mass, is going to be equal to what? M1, A1 plus M2, A2, and so on and so forth. But the right-hand side is what? MA is equal to the net force, right? So net force on 1 plus the net force on 2. This is then the net force on the system, right? Okay, so this is the net force on the system. If you think about it, forces on 1 can come from outside of the system, or it can come from 2. Or it can come from 2. 2 can act on 1. So the forces on 1, you will have external forces and the internal forces. Forces on 2, you may have force from 1 on 2, or you may have what? External forces. Well, what's this pair here? Force from 2 on 1, and force on 2 from 1. There are action and reaction forces, and they're going to be equal, right? So they cancel. Okay. So the internal forces cancel. If the internal forces cancel, this net force here is going to be the net external force. Okay. So you have the net external force, because the internal forces, they come in pair. 1 on 2, 2 on 1, 1 on 3, 3 on 1, they all. Okay, if the system is composed of multiple parts, then you have 1 on 2, 2 on 1. And if you have the 3 here, 1 on 3, 3 on 1, 2 on 3, 3 on 2, they all cancel. So the right-hand side is the net external force on the system. Okay, and that is then the concept from center of mass. Okay. So the left-hand side is then the total mass times the acceleration, and this is the acceleration of one particular point, the center of mass. And that's interesting there. All right, that's catching up on the idea of center of mass. Let's look at something that's not moving, for example. If this thing
Damn,
is
look
not
at that.
moving,
Look at this. That's just what I instead of like watching.
it's not moving. Okay. You may not want to be near it. So far, it's okay. So, if you get it, you come down a little bit and a little bit further, and at one point, starts to slide. Okay, tell me what angle it started to slide. Somewhere around there. Okay, okay. What's the angle there? What? How many? Look at that 30-degree there. Okay. The way it looks to me, it's more like something like this. Okay. The height is longer than the base here. So the angle here is really more than 45 degrees. Okay, make an estimate. Let's call it 55, for example. Okay, I decrease it and then 55 degrees starts to slide. Okay, so that's something we observe. 55 degrees. It starts. So that's all observation there.
I don't even take notes anymore. I just video swords.
And let's ask the question,
really
well,
lazy.
what's stopping it from sliding before that? What was holding it? How come it's not sliding it right now? Friction, very good. If the floor were icy, it's going to come down, right? Okay. So only the friction between the floor and the bottom of the plank that holds it there. What kind of friction is it? Static or kinetic?
Time for my next dose of allergy medicine.
So static friction here that is holding
I'm
it.
taking the medicine so nobody thinks I'm doing drugs.
So if we call it the critical angle, the critical angle is 55 degrees. And what do you think we want to find? Very good. Very good. You can find a coefficient of static friction. Yes?
Isn't there friction between the wall and the plank?
Okay. That's a very good question there. If you think about it, if there is friction here, in general there is, all right? We're going to take a case where it's a smooth wall. Reason being this, if it's sticky here, and this thing is starting to go, and the wall doesn't allow it to go, it's going to either go like this, and either go like there's going to be a buckle. Okay, so the plank would then be bent one way or the other. Okay, more like this, because it's holding it so that it cannot leave, right? In our case, the wall here is relative. Okay, it doesn't resist all that much. But we'll take a simple case. So there's a smooth there, smooth wall, and it doesn't forbid it to come down. Okay. You do have that consideration there in general. Yeah, you do have to consider that. All right. So let's see. We are looking for the coefficient of static friction between the floor and the bottom of the plank.
What did he just erase?
in order to solve this kind of problem, there are things that we need to observe about things that do not move. Okay? Right now, it's not moving. So for anything that's not moving, the velocity is constant. And since it's not moving, the angular velocity is also constant. And both are what? Both are zero. Okay, both are zero. And zero is a very special constant. If the velocity is constant, what's the acceleration? What? Zero. Has to be zero, right? And if the angular velocity is constant, what's the angular acceleration? Also zero. Okay. So, according to what we studied earlier, the net force is equal to ma. But if acceleration is zero, the net force has to be zero. For rotational motion, the net torque is equal to what? Net torque is equal to I alpha. I, rotational inertia, alpha, angular acceleration.
I'm
Right?
disappointed
So
he
that's
doesn't say alpha.
Newton's second law for rotational motion. And if alpha is equal to zero, then the net torque is going to be equal to zero. Therefore, if you see things that don't move, that are not interesting at all, the building, the bridges, the light fixture, things that don't move, okay? There are two conditions. Net force is going to be equal to zero, and the net torque also will be zero. So, okay, that's very important. The top one, we call it the translational equilibrium. Bottom one, we call it the rotational equilibrium.
So it's such a good excuse.
So rotate here, this plank is not moving. Right before it starts to fly, or when it moves. Therefore, we know what? The net force is equal to zero. The net torque is equal to zero. Right? So that's it. Right now, I don't know the mass, so let's estimate what kind of mass are we. Maybe talking about 30 kilograms or so. So let's just assume that the mass is something. Okay. And also assuming that it's uniform distribution there. Okay. The length is going to be what? 2 point. So the length is 2 point. Let's see. 2.5. Okay, make it 2.6 meters. Okay. Mass. Let's say 50 kilograms. Okay.
Yes.
All right. So, the center here is then 1.3 meter and 1.3 meter. The weight mg.
I dropped my phone. It's funny,
Down.
2 times I dropped my phone during when I was taking a video and I
suppose
heard
you
me
call it
cursing, dropping my phone on the phone, making a
the
lot of
weight
noise.
of the plank. And that's 50 times 9.8 mg. Considering the plank, the weight acts at the center, And we are assuming a wall that is smooth, so no friction along the wall, and we only have a normal force. So let's call that a normal force, M. The contact between the floor and the bottom of the plank,
Finish that while sending the video.
we would have a force. Okay. In general, you're going to have two components. One is the vertical, the other one is the horizontal. The vertical one here, so this is the normal force at the wall, and this is the normal force at the ground. Okay. Plus, there is a friction force. So you have something like that. And now let's use our condition. So we have two conditions. One, the net force is 0. The other, the net torque is equal to 0. From the net force equal to 0, how many equations do we have? Net force is equal to, we're going to get the x component of the left, 0. Y component of the left, also 0. So two equations, right? The x components here, we see that the ground support for the ground support force has only the vertical component. The weight has only the vertical component, and those do not have x component. So we see that the friction force is going to be equal to what? The normal force from the wall. Normal force from the wall. And the ground normal force is going to be equal to the weight, mg, right? It's going to be equal to mg. Are we okay so far? The coefficient of friction is the ratio of these two. Okay, so that's something to be found. And now we're done with the net force equal to 0. And we have used the x component, we have used the y component, 1 and 2. So we still have another condition, that is, this thing is not rotating, therefore the net torque is equal to 0. All right. This is then interesting. It's not rotating, so about what axis is it not rotating? Okay. It's
Trick
not
question.
rotating. It's not rotating about any axis. It's just not rotating, right? So you get your pick. And this is a nice thing about this kind of problem. If you choose the axis right, then you have less calculation. If you choose the axis not so smartly, then you have a lot of numbers. Okay, so here we go.
Me and Jeff from the YouTube video and the t-shirt pieces. There's no password, it's just algebra and trigonometry. Let me cover it.
If we consider this here, there are two forces acting at this point here, right? Remember, torque is R times F times sine of the angle. So each force is going to contribute a torque. if we take, for example, if I take an axis here, about this axis, how many forces would turn the plank clockwise?
That's gonna stay.
How many of the four forces, how many forces would turn the plank clockwise about the axis? It's only one. Which one?
Normal force.
Normal force at the ground, right?
That,
Turn
I was
the plank
guessing.
that way. And the other ones all turn it counterclockwise, right? So you have three counterclockwise torque and one clockwise torque. Are we okay there?
Yep.
Since you have four forces, you're gonna have four torques. Or we can make two of the torques vanish by choosing this axis. If I choose this axis here, these two forces contribute 0 torque. We agree. Now you have one force contribute counterclockwise and the other one contribute clockwise torque. Are we okay? All right. So then take the axis here.
I can't type with this watch on. I just have to
Choose
take it off to type.
axis here. Okay, perpendicular to the blackboard. Okay, perpendicular to the blackboard. That way, the weight turns it clockwise, and the normal force at the wall turns it counterclockwise. Are we okay? So, that would then be our third equation. Let's then calculate the torque from the weight. Torque from the weight is half the length. That's the R. Times the weight. Times the sine of an angle. So let me ask you what angle that is. Okay.
55 degrees.
Okay, the axis, from the axis to where the force acts, that's the R vector. And
I wouldn't even know.
the weight is the force, so this is the force vector. What's the angle between the two? You have a vector going that way, and you have a vector going this way. What's the angle between the two? The angle between the two is going to be this one, right? Okay, so that would be this one here. What would that be? 60?
There you go. I'm like,
See the
excuse me,
55
sir.
here?
It's like, he lied.
See the 55 here, so what is it going to be?
He got pissed.
145, right? Because you add 90 degrees to the 55. So it's going to be 145 degrees. And that's the clockwise torque. So this is the clockwise torque. And for the counterclockwise torque, counterclockwise torque is from the normal force at the wall. So the R goes all the way to here, and the force is that one. Right? Force is the normal force.
Sine 145.
So in this case, it's going to be that angle, right? Okay? So it's going to be the same angle again, right? Because you have also a 90 degree. Wait, not the same. Come on. This is a 55 degree. So what's that angle? 35 degree, right? Okay, so you add 90 to the 35. What do you have? 125. 125. So that's going to be the L times the normal force at the wall times sine of 125 degrees. And they
Oh, of course.
are
Probably thinks I'm a stalker.
supposed to be equal.
Like, who is this kid?
And they are supposed to be equal. So you see here then L would cancel, so let's rewrite it a little bit. 1/2 weight of the plank times sine of 145 degrees is equal to the normal force at the wall times sine of 125 degrees. Okay. But this here, let me see. This here is nothing but the friction force. Okay. This is equal to the friction force. Okay. So this is the friction force. And the weight of the plank is that the weight of the plank, this is the weight of the plank. Okay, is nothing but the normal force at the ground. Okay. So the weight of the plank, all right, so let me write it as F is equal to sine of 145 degrees over sine of 125 degrees. And here, this is 1/2. And then we divide both sides by the weight of the plank, which is equal to the normal force at the ground. Normal force at the ground. So this is the coefficient of static friction force. Okay. By definition, the friction force divided by the normal force. And therefore, the coefficient is given by this number here. All right? One can then use a calculator for this number. Let's see. So you get 125 and take a sine of that. And then divide by 125 sine of that. It's equal to something, and then divide by 2. And I get 0.35. So 0.35. You check my calculation, many times I have picked some, and I hit the wrong button. All right. Any question? Okay, to summarize, there are two conditions.
When I stood up at the
If you see
desk,
something
so
not
like
moving
lifted
at
the
all.
desk of the I was standing last time.
Something is not moving, net force is 0, net torque is equal to 0. And for the net torque, you get your choice, because it's not rotating, therefore it's not rotating about any axis. So you get your pick. If you pick the right axis, you have less calculation to do, because several of the torque may be 0. Okay.